Monsters, 8 explorable dungeons, 4 battle classes, and over 20,000 lines of code. I wrote my own 8-bit RPG for the Game Boy Color, featuring monsters from the D&D Monster Manual, and in this episode, I'm gonna show you how I did it. The premise is that you're an adventurer who's been locked in a dungeon, and you can't escape until you beat a series of floor bosses, each of which were lifted from the pages of the 2nd edition Dungeons & Dragons Monster Manual. As you explore the dungeon, you'll run into random encounters, solve puzzles, level up, and gain new abilities, with each floor getting a little more complex than the last. I knew this was going to be a pretty massive project, so I set aside a couple of months to work on it. Now, when it came to the coding, I was pretty sure I could get the job done, but when it came to the pixel art for all the monsters, I wasn't so sure on that one. So I found an artist that I'd worked with before on Fiverr. He was stoked to work on the project, and we were off to the races. Shout out to my supporters on Patreon. They paid for all of this amazing pixel art. Okay, with a general idea of what I was making and an asset pipeline established, I was ready to get coding. I could have used a game maker tool like GB Studio, but I was kind of stoked to work on my own game engine, so I decided to write the whole thing using C. There's a great tool called GBDK that combines a compiler with some libraries and a ton of examples that make it easy to get started with Game Boy programming. From a bird's eye view, the game's code is split into 2 major subsystems, one that handles the map and exploration, and another one to handle the first-person JRPG battles. And all of this code sat atop something called the core game engine, which sounds amazing, but it's actually kind of boring. Just like with modern games, retro games have a lot of assets, and the core game engine is primarily responsible for loading those assets into the system's working or video memory. It also handles the overall flow of the game's execution by swapping to different banks to run subsystem-specific code. For instance, in my game, most of the map code lives on bank 2, so that bank needs to be active in order for the map system to operate. Speaking of the map system, let's see how that works. Floor maps are broken down into 2 pieces, a tile map that defines the structure and shape of things, and a set of scripts and tables that define what's actually in the level. I created the tile maps using a program called Tile Map Studio, which is particularly suited to Game Boy development. The tiles it refers to are tiny 8x8 pixel images that form the basis for all graphics on the system. You store these tiles in the Game Boy's video memory and then compose them to create the game's background and foreground graphics. To make things easier, for backgrounds, you'll often store a grid of tile IDs directly in the ROM as a list of bytes called a tile map. Tile Map Studio lets you make these tile maps visually, then save them as binary data, which you can easily shove into your ROM and load at runtime. And this is the normal way that you use the program. You create a mock tile set that represents how you expect the data to be loaded at runtime, and then draw each individual tile. But in my game, and many games, this is overkill because background tiles are always drawn in groups of 4. Put another way, my game uses a 16x16 pixel grid instead of an 8x8, meaning I don't have to draw each individual tile. Instead, I use a mock tile set to denote the core level blocks, things like walls, doors, decorations, and so on. Then, at runtime, instead of directly drawing each tile map, I expand each tile into a 16x16 pixel block of graphics. A cool side effect of using this approach is that I actually have to use 4 times less data to store each of the blocks, meaning I can store some game information in the remaining 2 bits. Originally, I limited maps to only use 16x16 of these blocks, but it felt really limited. So I decided to scrap the approach and did something that's kind of like stream loading. This is a really common pattern in 8-bit games, with the idea being to load the tiles on the leading edge as the player moves in a particular direction. For my game, the implementation was pretty simple. Since the player takes 16 frames to move from block to block, all I had to do was render a block for each frame, and by the time I was done, I will have rendered the entire leading edge. And this worked great, until I ran into a pretty serious problem. So the scripts for each of these maps defines a bunch of different game objects. I have things like chests, doors, sconces that you can light, so on and so forth. When I was first programming the game, I didn't have many of these objects, but towards the end, I ended up with 7 distinct objects, some of which could have arbitrarily long lists of items. Now, when I was pre-computing all of the data for the leading edge, I had to go through all of these lists one by one to figure out if there was a game object at this particular point. This is important because if there's a game object that has state at that position, I need to know what that state is. A chest, for instance, if you've already opened it, it needs to be rendered as open instead of its default way, which would be closed. My first approach was to just brute force it. I just searched through all of the items and all the lists until I found an item that was at the same location for the one that I needed to render. This works great if there's only a few game objects, but as the levels grew more complex, it actually got really slow. The issue here is that I needed to compute the data for each position in the buffer between frames. And if I was going through every single object in the level for each of those buffer tiles, it would just be too slow. What I really needed was an interface that I could give some map coordinates, and it would tell me if there was any objects at that position in the map. What I needed was a hash table. Technically speaking, what a hash table does is take a bunch of information, like a string or some map coordinates, and map it down to a single integer that can be used as an index to an array. As long as the hashing function, which takes the large amount of data and produces that integer, is fast, then accessing and setting data will also be fast. A good hashing function will evenly distribute the numbers it generates across each of the entries in the table, and will choose different numbers even if the input values only change a little. But unless you know all of the data up front and do the mappings by hand, no hashing function will be perfect, meaning you'll have collisions. There are a lot of ways to handle this, and for my implementation, I chose to use buckets. Instead of storing the game objects directly in the table, each entry is a linked list that stores a bucket of objects, meaning when I need to look something up, I may need to rifle through the bucket to find the exact object I'm looking for. But that takes way less time than going through all of the objects in the map. The way I ended up using the hash table was to store all of the game objects in it when the map was initialized. Then I could very quickly determine if there was anything at that position in the map when I was doing the game's logic or filling that leading edge buffer. One important note here is that the linked lists I was using as buckets, they require something called dynamic memory allocation. For this, you have a section of the memory called the heap, which is dynamically divvied up as needed when the program is running. A lot of sources online will tell you to avoid doing this when programming for things like the NES or the Game Boy, and for the most part, they're right. The method can be really slow and cause a bunch of weird errors if you don't manually free all the memory that you've allocated. In my case, I've used dynamic memory allocation like this before in C, and since I was only using it in one spot, I was pretty confident that I could clean up after myself. Okay, that's enough about the map system. It's time to battle. The battle system was just as complex as the map system, but
Alright, here are some quick steps to get you from nothing to making a game as fast as possible, even if you work a full-time job like me. I'm a teacher, and I started here with this Pico 8 game. I remade it 4 times, and now I have this, which is a demo you can check out. Links in the description. There's a little bit of credibility to prove I know what I'm talking about. Now, I got from here to here in just about 2 years. That might sound like a long time to you, but I got from here to here in a week with minimal tutorial. Learning game dev can be fast and fun if you do it the right way, and that's what I'm going to try to teach you today. Step 1, start with Pico 8. I know Godot is in the thumbnail, and we'll get to Godot, but I highly suggest starting with Pico 8. Here's why. Game development is hard. The learning curve is very high, and because of this, it's very easy to get discouraged and quit. I quit a few times when I first started in Unity because there was so much to learn and it felt impossible without having any programming background. In order to stick with game dev, you need to actually make things you can play while you're making them. This feedback loop will keep you encouraged to keep learning so that you feel excited to add more things to your game. If you get caught up in tutorial purgatory and never have any freedom to actually play with what you make and feel like you understand it, you'll be
Ah. Can't. Thing is I know this stuff. I'm gonna stop for now.